Welcome to our video on encryption. Today we'll dive into the essentials of encryption, covering what encryption is, its types, comparisons, algorithm selection, key management, plus we'll show hands-on demos with AES and RSA. Encryption powers tools you use every day. Think secure WhatsApp chats, VPNs, or cryptocurrency transactions. Let's unlock the secrets of keeping your data safe. Encryption is like a secret code that protects your messages. Imagine writing a note to a friend that you don't want anyone else to read. You scramble the letters in a special way, and only your friend, who knows the trick, can unscramble it. Encryption does this for texts, emails, or videos, ensuring only the right people can access the information. In cryptography, the original message is called plaintext. The process of scrambling it is encryption, and unscrambling it is decryption. The scrambled result is ciphertext. A cryptographic key is the secret used with an algorithm to encrypt or decrypt data. Let's explore further. Encryption comes in two main flavors, symmetric and asymmetric. Symmetric encryption uses one key for both encryption and decryption. It's like a shared password that both parties need. Asymmetric encryption uses a pair of keys, a public key to encrypt and a private key to decrypt. Think of a mailbox. Anyone can drop a letter using the public key, but only the owner with the private key can open it. Let's compare symmetric and asymmetric encryption. Symmetric encryption. Speed, fast, ideal for large data like files or databases. Key management. Tricky, as the same key must be securely shared. Examples: AES, DES. Use case: securing data at rest, like encrypting a hard drive or VPN connection. Asymmetric encryption. Speed: slower. Better for small data, like emails or authentication. Key management. Easier, as public keys can be shared openly, while private keys stay secret. Examples: RSA, ECC. Use case: secure communication, like HTTPS for websites, or end-to-end encrypted chats in WhatsApp. Symmetric is faster but needs secure key sharing. Asymmetric is slower but simplifies key distribution. If you're sharing keys with a third party, asymmetric is usually the way to go. In the real world, systems like HTTPS combine both. Asymmetric encryption securely exchanges a symmetric key, which then encrypts the bulk of the data for speed. This gives you secure key sharing and fast performance. Think of it as the best of both worlds. So, you've decided whether to use symmetric or asymmetric encryption. Great! But now comes the next big question. Which algorithm should you choose? Let's break it down step by step in a way that's easy to follow. First things first, always check with your company's security team and review their security policies. Some industries, like government systems or payment processing, have strict compliance requirements, such as FIPS 140 or PCI DSS. Following these standards is non-negotiable. If you're not bound by specific regulations, you'll want to ensure your chosen algorithm is safe and trusted. A great place to start is NIST Cryptographic Algorithm Validation Program. Let's take a quick look at their website. Here we are on the NIST website. It provides validation testing of approved cryptographic algorithms and their individual components. You'll find a list of validated algorithms in SP 800-140C document. Here we are on the document. We can see AES is on the list, so it's a safe bet for symmetric encryption. Triple DES is also listed, but it's only approved for decryption, not encryption, so avoid using it for new encryption tasks. But picking an algorithm isn't the whole story. You also need to consider factors like key size, cipher modes, and padding schemes. NIST publications have all the details. But if you're like me and prefer a quicker approach, head over to my go-to resource, AES Cryptographic Storage Cheat Sheet. Let's dive into the cheat sheet's algorithms section. For symmetric encryption, it recommends AES with a key size of at least 128 bits, ideally 256 bits, for maximum security. You'll also need to choose a secure cipher mode. The preferred modes are GCM and CCM, but CTR or CBC with separate authentication techniques like encrypt, then MAC are solid alternatives if needed. And ECB should not be used outside of very specific circumstances. Now let's talk about asymmetric encryption. The cheat sheet highlights ECC as the preferred algorithm. If ECC isn't an option and you need to use RSA, make sure the key size is at least 2048 bits. Also, for RSA, always enable random padding, known as OAEP. There's a ton of valuable information in the OWASP cheat sheet, so I highly recommend checking it out. The link can be found in the description box below. Here's the quick summary as of today, July 2025. Keys are the heart of encryption. If you lose them, your data could be locked forever or exposed. Here's how to manage them. Secure storage. Store keys in hardware security modules, HSMs, or encrypted key vaults. Never store them in plain text or push to platforms like GitHub. Key rotation. Update keys regularly to limit damage if one is compromised. Key distribution. For symmetric keys, use secure channels like Diffie-Hellman or asymmetric encryption. For asymmetric, share public keys via trusted directories. Access control. Restrict key access with role-based permissions with the principle of least privilege and keep audit logs. Secure key generation. Keys and initialization vectors must use cryptographically secure random number generators, like those in OpenSSL. Weak randomness makes encryption predictable and easier to crack. Backup. Keep encrypted backups of keys, ensuring they're as secure as the originals. Let's put theory into action with an AES demo using OpenSSL and an online tool. Here we are on an online AES tool. Here we'll select AES with CBC mode, since OpenSSL doesn't support GCM here. Choose a 256-bit key for maximum security and keep the output in base64 format. Let the tool generate a random IV and secret key for us. Type the message Tim can code, click Encrypt, and we get a base64 encoded ciphertext. Now, let's decrypt it in a terminal. Windows and Mac users can follow, but Windows needs OpenSSL installed. Save the key, IV, and ciphertext as variables, then run the OpenSSL command. This decrypts the ciphertext, revealing Tim can code. Now, let's try asymmetric encryption with RSA. Click Generate Key to create a public-private key pair. The private key is for decryption and must stay secure. The public key is for encryption and can be shared. In the terminal, save the public key to public_key.pem. Then, encrypt the message "Can Tim code" with the command here. Then convert the output to base64 and copy the string. Back in the online tool, paste the ciphertext. And get the private key on the above. Then click Decrypt. There's our message. Can Tim code? So, there you have it. By understanding these concepts, you're ready to make smart choices to secure your data. Thanks for watching. Hope you find this video helpful, and check the links in the description for NIST, OWASP, and more resources.